Today we will talk about advanced topics in stability. Previously, we talked about the numerical method used to check the stability of a structure. The method was based on the comparison between the number of unknowns and the number of equilibrium equations. We said that if the number of equilibrium equations was less or equal to the number of unknowns, then the structure is probably stable. So why do we say probably stable? Why do we have doubt about the stability of the structure, although the comparison between the unknowns and the equations indicates that the structure is stable? Are there cases when this stability check will not work? In this video, we will show cases where the numerical stability check will indicate that the structure is stable, but in reality, it is not. Let us examine the first example. By examining the shown frame, we find that it has two fixed supports with 6 reactions. It is an open frame with no internal unknowns, so the total number of unknowns is 6. Because the frame has no hinges, the number of equilibrium equations is 3. By comparison, the number of unknowns is larger than the number of equations, so the structure is stable and indeterminate, according to the numerical check, and in reality, it is stable. Suppose we take the previous frame and add another part to its right, as shown. Let us examine the changes that will occur. First, the number of unknowns will be increased by 1 due to the addition of the roller support at C. The equilibrium equations will also be increased by 2 due to the added 2 hinges. After this addition, the number of unknowns is still higher than the number of equations, which, according to the numerical stability check, indicates a stable structure. In reality, however, the structure is unstable. Instability occurs in the added part, as shown by the failure mechanism. It is considered a local instability because instability occurs in only a part of the structure. Now let us look at another case. When all the reactions are in one direction, as shown in the following frame, any force perpendicular to that direction can cause instability irrespective of the number of reactions. The shown frame has 3 reactions in the vertical direction due to 3 roller supports. The number of unknowns is equal to the number of equilibrium equations, which is equal to 3. This should indicate a stable structure according to the stability check rules. In reality, however, this frame is unstable. The instability can be easily visualized when the frame is subjected to a horizontal force because no support in the horizontal direction is present to resist this force. Another case of instability occurs when the number of external unknowns, the reactions, is not enough. Consider the following frame. It has 2 reactions and 3 internal unknowns due to the closed frame. The total unknowns is 5. Although the number of unknowns is greater than the number of equilibrium equations, the structure is actually unstable because it only has 2 reactions. We need at least 3 reactions to attain stability. The stability mechanism can be visualized as shown. Let us examine another example in which the numerical stability check fails. Take a look at the following truss. The truss has 3 reactions and 19 truss elements, giving 22 unknowns. This is equal to the equilibrium equations, which is also 22. According to the rule given earlier, this should lead to a stable truss. But in reality, this truss is unstable. This is due to the presence of the quad loop in the truss, which is the source of instability. The source of instability can be easily confirmed by watching the instability mechanism of the truss. Finally, let us consider the following example. The shown closed frame has 3 reactions. So the total number of unknowns is 6. 3 reactions plus 3 internal unknowns. Because we only have 3 equilibrium equations, which is far less than the number of unknowns, this frame should be stable according to the rule. However, this frame is unstable. Let us investigate the reasons for this instability. By taking a closer look at the reactions, we will discover that all the reactions are concurrent and will all meet at point A. Therefore, these reactions will not be able to resist any force that is trying to rotate the frame around point A. This can be confirmed by the shown instability mechanism. In conclusion, it should be emphasized that the numerical method of investigating stability using the comparison between the number of unknowns and the number of equilibrium equations is very useful. But it is not conclusive and fails to discover instability in several occasions. Therefore, it should be used to check stability as a first step, followed by inspection by an experienced structural engineer, or by employing more complex methods to check stability.